Okay, let's start. First, let's review what we had in the last lecture. Review. Okay, last time we talked roughly about the ocean environment. I said a few things about the marine structures, and also 3 main sources, environmental sources that excites the marine structures, and that's waves, current, and wind. Then this is introduction. Then I showed you a few examples about dimensional analysis, and we I talked about Reynolds number, Froude number, and that's the ratio of every 2 of the 3 principal forces: inertial force, viscous force, and gravitational force. And then I made a quick review of linear wave theory, the basics, the assumptions, a governing equation, which is the Laplace equation, another form of continuity equation. And then we had the boundary conditions, free surface boundary condition, C bottom. And then we go over the solutions, and I showed you a picture of the trajectories for deep water, shallow water, and the intermediate depth water. And then we went through the ocean waves, a few categories, and one important concept is it's a random process. We have to use random variables, and like, is this one better? Yes. Okay, to describe the ocean waves, we have the mean, variance, and a few other things. And at the end, we went through what is a wave spectra, right? And from this lecture, is the microphone work here? I don't know. Did I turn it on? Off. I think it's on. Okay. And this lecture, I'm gonna talk about the short-term and long-term statistics of ocean waves, and then we're gonna do the wave loading, Martin equation. So this is a typical measurement from the ocean. There are many ways to define a wave period. This is defined by 2 wave crest, Tc, and also we can define the wave period by finding the consecutive up zero crossing, this point and this point. This is called zero a wave period, determined by the 0 crossings, and also the maximum wave height and the definition of wave height is like this. It's very straightforward. And a very important concept is the significant wave height. Short, long-term wave statistics. Significant wave height. It is defined as the average of the 1/3 highest waves. If you have a measurement, I have determined a wave height as h1. Of course, from my measurement, I'm gonna have many of this h1, 2, 3, till infinity. Now I order those. I find the largest one here from this. This is called a sample, and many. Okay. Then I find the next, the second largest one, and the third largest one, until n, which is the smallest one. This is I'm ordering, from the highest to from the largest to the smallest. And then, okay, this is 1/3 of the total samples. Suppose this is n equals to 300. Okay, then I have 100. This is 1/3 of the total samples. This is for example. Now, significant wave height is defined as summation of hi, right? The mean of this portion. Why we have this definition? Because it's very important. It's associated with the wave statistics, and the origin of this definition is mathematically is defined this way, but in reality, in the old times, the mariners, the sailors, when they are standing on the boat, when they look at the waves comes and go. Those guys are very experienced. They can tell how high the wave is. If you let him sitting there and observe for like 1 or 2 hours, and he'll give you a wave height. This wave height from this experienced guy happens to be very close to this definition. So this is why we call it a significant wave height. And the second thing I'm going to introduce is the PDF probability distribution function of the surface elevation. If we have a measurement at a given location, 8 of t, just like this. This is a continuous profile, but in measurement we have many points along these curves. Okay, if we plot this thing, we do statistical analysis, we'll find the distribution of the surface elevation follows a Gaussian distribution, which is the normal distribution, and with the zero mean. Okay, the mathematical form of this is 2 pi sigma eta exponential here sigma eta is the variance, which is what, right? This is supposed to be that's a mean, right? Mean squared than this, but it's since the mean of this is 0, it's just like this. No. Now we should put it here. Okay. This is nothing but integration of eta squared dx, right? Or dt, if we're talking about time. And this is PDF of surface elevation. Now we're talking about the PDF of wave amplitude or wave height. So for a narrow band spectra, and if the surface elevation follow a Gaussian distribution or normal distribution, and we can prove theoretically the wave amplitude follows the Rayleigh distribution, which is like this. For A equals to equal and greater than 0. Here M now is defined like this. If we define Mi is called the spectral moment. Infinity omega I. This is the given spectra, and this is the frequency, and this is I is corresponding. This is called the IS spectral moment. Okay, here M now means this I equals to 0. That is M now S omega d omega. Okay. And then the cumulative PDF is, that's the, if we do an integration for this with this distribution, we'll find, okay, 1 minus exp those are just mathematics. If you have interest, or in the future you need to use those formulas, you can find it from any reference books, and in fact you can do this if you have know this, you can derive this by yourself. Now I just want to tell you those equations. And one thing I want to say is here, this m now is equal to the spectral integration. This is energy spectra. The integration of all the spectra gives you the area under the spectra and the curve. That means the total energy, right? How about this sigma squared variance, right? What is this? This is also the total energy, 8 squared. If you have a sinusoidal wave, right? Amplitude is A, right? The energy of this thing is proportional to A squared, right? The integration of 8 squared is also the total energy. What does that mean? That means m now equals to sigma squared. That's a very straightforward thing. It's just based on conservation of energy. Okay. So now if I give you a wave spectra and want you to find a few things. Let's see the statistics in frequency domain. Okay, I give you this spectra. This is omega. This is energy. And we know the wave amplitude follows a Rayleigh distribution. And then we can write the significant wave height in terms of the m now, which is the integration, right? And it's here. If we have time by the end of this lecture, I'm gonna show you how we derive this. There are rigorous theoretical derivation of this thing, but so now I just want to show you this this result. Okay. Long-term C-state. So how long-term? This is one. This is another topic. So in reality, what we had, what I showed you is just short term. Before, like 2-3 hours, the statistics is based on 2-3 hours measurement. But in reality, when we design a marine structure, we want to, probably want the structure sitting there for like 20 years, 40 years, or maybe 100 years. So for design purpose, those short-term description of the ocean waves is not enough. So we have a long-term C-state. And unfortunately, we do not have enough data for the long-term statistic description of the ocean waves. So all the long-term, like PDFs, CPDFs, are based on the short-term measurements. So now I'm going to introduce you a very important concept is called the design extreme value of wave height. Design extreme value. Suppose now, okay, I have a structure. I make a design, and then I want this structure sitting in this specific area for 100 years in operation without any dangers. The number one thing that I want to figure out is during these 100 years, given us probability, how large, what is the largest wave height waves gonna show up in this area? So I have to know that in order to do quite a few things, like design the air gap. That's we have a structure like a spar or something. We have whatever on the top. This is a spar, have waves. I want to know the height of this. It's called air gap or the dry draft. So in order to do this, I want to know the largest waves that's going to show up in this area. So that's called the design extreme value. So how do we figure that out? We use the so-called Rayleigh distribution, what I just introduced to you. Okay, typically the design extreme value of the wave height, H design value, is the wave amplitude that has a probability of 0.01 that can be exceeded in n counters. N is a large value. That means in n number of waves, the amplitude of the waves less than a half of the wave height less than this design value, that probability is 1 minus 0.01 is 0.99. Okay, that's how we define this design extreme value. Of course, you can make larger requirements, more strict requirements, like 0.01, right? But as you will find out that this value is not as important as the M now, which I will show you later. Okay, let's say this is 0.01. So what do we have for the CPDF for the wave height or wave amplitude? That is F A 1 minus AXP, right? This is the Rayleigh distribution of the wave amplitude. Now we want a wave. We want the design value of this be less than all the waves in n number of waves, the amplitude smaller than this value, the probability is 0.01. So if we write this in mathematically, is like this. One Okay. Here P is the probability of this thing. P is like this. For one wave that is lower than this design value is P. For n numbers of waves, then in this n number of waves, at least one wave amplitude will becomes larger than this design value. Is this probability, and it's like this. Okay, we set this equals to 0.01, right? This was our design criteria. So I just then if we do the math here, P is equals to 0.99 1 over n, right? This thing equals to 0.01. If we move this to this side and this to this side, that's P 0.99 equals to P to the nth, right? Nth power, and then P equals to this thing. And on the other hand, we know P is equal to P is equal to this guy. This is the Rayleigh distribution. Okay, this guy equals to 1. This is the Rayleigh distribution, right? So if we solve for A, what we end up is A, this is the design value we want, amplitude. Okay, we end up with this design value. And if you put any numbers like n here, try different values, and let's say 1,000 or 10,000, and keep the rest of the parameters unchanged, you'll find the change, although you change n in 10 times, the variation in this design value is about 10%. So we can see this design value is not very sensitive to this n number, this n. You can try this out, after class. So we can make an approximation, this value, based on Taylor expansion. We expand this part. We'll have a design value approximately equals to n over 100. Okay. And since we know then the design wave height is just double of the amplitude, right? Since we know the significant wave height is approximately 4 times, right? Is 4.0048, and then we can find the ratio of design value over HS is approximately square root this is a very important thing you need to know. Okay. Now, if for a 100-year design period, if we assume an average wave period of 8 seconds, and we know the significant wave height is suppose like 10 meter, so how are we going to find this design wave height? It's pretty straightforward, right? If we have 100 years requirement, it's called 100-year wave in this scenario. 100 years plus 365 days, 24 hours, and this many seconds divided by average wave period, let's say 8 seconds, and this will give us a number of waves during the life of this structure that the structure will encounter. So from this equation we plug in n and we figure out design value over significant height is 3.494, right? And this is 10 meter. So our design value is about 35 meters, right? Okay. Now you have an idea about what is the design extreme wave height, and you also know in the design process we need simulate the ocean waves, and so I'm gonna introduce you another method. It's called random phase and random amplitude method. To simulate ocean waves. This is based on the assumption of linear superposition. That means we assume the ocean waves can be decomposed into many components. The formula we use here is very simple. It's a linear superposition of many components, many individual sinusoidal waves so we assume the sea surface can be approximated with this equation. K is the wave number, wave frequency, and those follow the dispersion relation. And the unknown in this formula is the amplitude and the phase. These two are the unknowns. So give you a wave spectra. How do you simulate the random ocean waves? We can use the given wave spectra to figure out this amplitude. So if we divided this spectra to many components, divisions, this part corresponding wave frequency omega g, and this is the energy of this wave components carry. So if we use this is the energy these components of waves carries, and that components, the energy can also be written as this is if you have a sinusoidal wave of amplitude a cosine kx or something, then the energy is like this, right? A squared. There's a and for a squared over 4 is the one part is the kinetic energy, the other part is the potential energy, right? The equipartition. So gives you a half. This you have learned from your linear wave theory. Okay, so we have solved Aj equals to okay. So the only unknown left here is the phase. How do we get the phase? We don't know how. So, but we know the ocean waves is a random process and follow normal distribution. So what we're gonna do is we generate a random phase randomly from so this phase is in the range of 0 to 2 pi. At each of these components, I generate a random number. I don't know how large it is, but each I can use the built-in program like in MATLAB or other subroutines to generate this number. The only rule we have is in this range. It follows the normal distribution. Okay, then now we have all those numbers we can plug in, and so if you have enough components, say okay, this n goes to 1,000 or even higher, 5,000 or 10,000, and then you can generate random surface waves, right? And those waves are the ocean waves that we want to simulate. So that means each time you run a simulation, this waves is probably different. But is that something acceptable? Think about it. Is that something acceptable? This is number one. This is the first run. If I have a second run, it's like this. So what's happening? We're generating different random waves. Why is that? But the thing we are considered here is not the individual surface elevations. It's statistics. If you do statistical analysis, those two surface elevation, if you follow the strict procedures, will both follow the normal distribution. And if you do you figure out, use FFT or whatever to figure out its spectra, it is this spectra. So this is the reality in the ocean. If you put a probe at one space, do a measurement, and then you put another probe, do a measurement, you possibly get two different sets of results. But the important thing is statistics, and it's energy carried here. Energy spectra is the same. So that's the important thing. That means the phase, when we do this, we just arbitrarily put a phase in there. Why is that? Because when we generated this spectra, we already throw the phase information away. This is the way we do simulate the random waves. Once you have this random surface elevation, you can compute the velocity, right? Each component of this sinusoidal wave gives you a velocity, and then you do similar thing, linear superposition, to sum those velocities up. Let me find another marker. Oh, this one is better. Okay, we have this is now is known, and we have u x of t summation j to n same thing here, right? This is the horizontal velocity, and we have vertical velocity, right? Same summation AG, same thing. This is sense, okay? And we can, keep going to find the acceleration. This is important because we need the velocity to compute the forces, and we need the acceleration to compute the forces. Okay, this is the linear superposition. If you want to go higher to the second order terms, what are you going to do? You're going to include not only this linear part, the wave and waves interact. You're going to consider the sum frequency term and the difference frequency term, which is like this is kg, and I have ki, the other term. So we're going to consider kg minus ki, kg plus ki. Those are called sum difference frequency terms. Those are second order effects. We're not going to discuss this in this lecture. So this figure shows you, visually or clearly how did you do this thing. And this is the wave spectra. You can divide it into many components, and each of these components you figure out amplitude of this wave, and you generate those sinusoidal waves, and then you sum this up at one location, you get these random surface waves. The second method we do, this is a very simple strategy, and we like it because it's easy to use. People can understand this method easily, but the drawback is we have to use a large number of wave components in order to achieve the normal distribution. What if I only have just a few? Let's see, this is random phase and random amplitude. The second method is to do this with the random amplitude. You can see this is a random phase. You generate random numbers. And the random amplitude, you can easily guess we are doing the similar thing with the amplitude. So instead of setting the phase information to be random, now we setting the amplitude. These two follow a normal distribution, and with the mean equal to 0, and variation is like this. It's actually the similar concept. We still divide this into many components. Instead of using the amplitude as determined with this as the amplitude, we use this as a control input to the normal distribution of, we say AJ is follow, and BJ similar thing. So reality shows if we have enough components for these two methods, we have similar results in terms of the wave number, the wave frequency spectra, and the generated waves distribution. Personally, I like this one better. Okay, now we are almost done with the wave parts. So why did I spend this much of time doing the waves? Because in order to compute the wave forces, we want to simulate the waves first, and in application. Application methods to simulate the wave environment in real design. Okay, the first method as I said, okay, we have we can use random phase or random amplitude method to simulate the a storm condition in in a short time. We construct random waves. Okay, that's what I told you. And then second, maybe we want to select a single frequency wave. Single wave with some period and amplitude that we are interested, and we can do this. This is called short-term simulation. Those are 2-hour, 3-hour simulations. And another way we do simulate the waves in real design is figure out the extreme value in design. It's called design extreme value. This what we just went through is like we have 100-year wave or 20-year wave. You use the relationship between the significant wave height, and you know to figure out. And another important thing is the fatigue of the structures in the lifespan. We may specify a certain threshold of the wave height, and then we say, okay, once the wave height goes beyond this threshold value, gonna introduce a stress that is valid for our fatigue analysis. In fatigue, we need to count the number of the cycles of the forces, and so to do that we need to specify a value, a threshold. Threshold. How do I spell threshold? For fatigue analysis. Okay. So this is the 4 typical ways we need to consider in simulating waves. So the most common ones are this thing and this thing, 1 and 3. This is short term, those are long term. We're talking about 100-year waves or things like this. Okay, next topic would be on the frequency scales of wave excitation on ocean systems. I'm sure you all had a structure dynamics class, right? You have a structure, you have forces. The important thing is the frequencies of the exciting force, right? If the frequency of external force matches the natural frequency of the structure, you have a resonance. You expect a large response from the structure. And in design, in reality, you want to avoid that that scenario. So in the ocean, the marine dynamics, marine hydrodynamics, and we also have this problem. This is a given wave spectra like this, and we have a few. If the excitement force is in this area, the response from the structure can be ring, spring, those high frequency response. And what is a ring and spring? That's the high frequency force. Like when we have water, the water and the ship bottom impact, slam together, and you have this high oscillation force. So ring is like why it's called ring? It's decayed. You see this the trend. It's like you use a hammer to knock a ring, a bell. It goes ring. So from the amplitude, it goes smaller. That's called ring. And the spring is like you force the structure to move, and it's sort of a steady state. It's like spring. It's if there's no extra thing, the decay is sort of steady state, and this whipping and straining is like ringing is transition state of this force. Okay, and this is the wave frequency motion, the motion of the structure caused by the wave components that carries the most of the energy of the sea in this area. And we also have slow drift motion. That's like we have long waves and also like swells that goes very slow. The structure does not respond dynamically, and but we have like you have a mod structure here and this, and you have long waves coming this way, and then the structure will move to this part, and this is a very slow process, and then comes back. The typical period of this is probably like larger than 25 seconds. And also we have mean drift. That is if the current and wind and wave gives you like a sort of a permanent displacement from where it should be, that's called mean drift. Okay, yeah. In offshore engineering, this is called a high frequency response, wave frequency response, and this is a low frequency. So typically three ranges, and those are the low frequency. Those is the wave frequency responses. Okay, enough background. Now let's look at the wave forces on ocean systems. Wave forces. Okay, the first thing is hydrostatic. So here, this is a illustration of the coordinate system and this wetted area. So we have two coordinate systems. One is this one, and the other is this one, fixed with the ship section. We use two coordinate system because this is XYZ prime. If we have this, because it makes things easier when we calculate the hydrostatic properties. And for the Earth fixed coordinate system here, we have this because it's easier to express Newton's second law and wave properties. This is inertia frame. Okay, and then the relationship between these two coordinates or transformation from one system to another can be written as this. R is a vector. 2, 3, 4, 5, 6. Okay. 4, 5, 6 means the rotational this rotational angle. So the total force would be the integration on this weighted surface times integration of this thing. This is pressure. This is the normal vector pointing inward to the body. This is very straightforward, right? If we know all those, we know the pressure, we know the normal vector at any point of here, we do the integration, then we get a force, right? And also the momentum. This is pressure. Cross product of the normal vector gives you the moment. For hydrostatic form, what is pressure? Pressure is nothing else but right? Rho Gz. So that's the pressure from water. If you plug in these things, and you can easily find the hydrostatic. This is hydrostatic pressure, hydrostatic force and moments. And typically, if this instantaneous wet surface is hard to compute. For simplicity, we just use the mean water wet surface. That is, instead of tracking this green area, we track the z equal to 0, this line, and the body structure, this section. But this is for small motions. If we have large motions, this approximation does not provide good accurate enough results. We have to track this surface area, which is a very hard problem. Okay, this is hydrodynamic. So if we figure out the hydrodynamic pressure and then use these two formulas, we can compute the hydrodynamic forces. but the dynamic pressure and moments introduce the pressure force and moments are not very easy to figure out. So we have three typical methods we use to compute these loads. The three method here is loads hydrodynamic is Morrison equation, Krylov, and then this diffraction theory. Why do we separate it? Because this is a too completed problem. It has to do with the scales, the relative scales of the structure and the waves. There's it's very hard, difficult to find a general formulation for all those scenarios. So we decide, based on experience and dimensional analysis, we decide to use these three methods to compute the hydrodynamic loads. So for the Morrison equation, this is the case where the inertial force and the viscous force are, approximately equally important. We cannot ignore, any of them. And also in this scenario, we require the structure is the characteristic scale of the structure is relatively small, so that the diffraction of the waves from the structure is minimal. This Krylov method is used when let me write this down. Viscous is important. Inertial force is important, and characteristic scales of the structure, I use D, is small. For the Krylov effect, we're going to require viscous force. We assume it's small. We don't use, we can ignore it. Inertial force is there we have to consider. And then the characteristic geometry of the structure is small. And this diffraction theory, what we have is we also ignore the viscous force. We keep the inertial force, and the structure of the characteristic geometry of the structure can be large and also can be small and large. So there's no specific requirements on this thing. So how do we end up with this this thing? I want to put those things in a legitimate way, and that's dimensional analysis. Okay. So it's very important for us to understand why we have three different methods, and in which skill each one is applicable. So that's what we're trying to do with the dimension analysis. Assume the force on a structure is a function of the characteristic of scale of the structure, wavelength lambda, wave period t, characteristic velocity, and rho density nu. This is the kinematic viscosity and a time scale, right? And if you follow the dimensional analysis, you can easily end up with this thing. The non-dimensional force is a function of here. Let me use another symbol. This is too confusing. Okay, G U now D mu U now T D pi D over lambda T over capital T, right? This is what? Reynolds number, which is the ratio of inertial force to viscous force, and this is called the Keogan-Carpenter number, which is the so-called Kissy number, and this number is the diffraction parameter. Diffraction number, and this is the dimensionless time. If we use linear wave theory, what is U now? So U now equals to omega A, right? Omega H over 2. And it also equals to pi H over T, right? So simply see, okay, the angular frequency is here, and this is the A, and this is omega. So the velocity at this point is omega A. That's you have a wave like this, right? It's very straightforward. Okay, with this, the Kc number becomes, Kc number is U now T over D pi H over D, right? This is the scale of the water particle orbital length to the body diameter, which is the wave height over the characteristic scale of the structure. Okay, with and also another number is the diffraction number, is pi d over lambda. So this is the two important numbers. And let's see this picture. This goes the Kc number, this goes the diffractional number. So when the size of the body is large compared to the wavelength that goes to this way, d over lambda. That means the structure is likely to diffract the waves. What is diffract? Diffract is like influence the wave field. If this is a wall, incoming waves goes hit the wall and then reflect back. This is called the diffraction. Or the structure is large enough, the waves change direction, go around it. This is called the diffraction. If the structure is very small, here, instead of a wall, I put this pen there. The waves probably gonna come by. It doesn't see much of this pen. So the relative size of the structure and the wavelength is important. So goes this way, we use diffraction theory. And if the Kc number increase, that is the wave height over the structure scale is large, and the viscous effect becomes important, and viscous force cannot be neglected in this area. So in this region, both Kc and diffraction number is small, are small, so we can use the Freud-Krylov and the diffractional theory to compute the wave forces. So the magnitude of these lines is determined from experiments and many years of experience in our industry. And so you can see 1, 2, 3. These three regions. How about this region? This region, none of those simplifications methods works. But however, you see this hyperbola, this curve, means h over lambda equals to 0.1418. That's the limitation of linear waves. Beyond this curve goes this way, the wave breaks. So in reality, we do not have much problem in here. So apply those things. So most of the problem are focusing in this region. Wow. I'm gonna use about 10 minutes to introduce to you the Morrison equation. Okay, when we talk about Morrison equation, we should know those in this region means small diffraction number, large Kc number. The assumption of Morrison equation, the Morrison equation. So this equation is first used by a bunch of guys: Morrison, O'Brien, Johnson, and Schiff in, make your best guess, which year? 1950. So we still use results from about half a century ago. So it's your guys' responsibility to improve these things. Okay. Okay. What they assumed is fairly simple. So they assume the total force on a surface-appearing cylinder structure shown here in a wave field. The force on this structure can be divided into two portions. One is the inertial force, dFi, I will call it, and then the other is viscous force. Or we see the drag So then the total force dF total dFi plus dFd. So how do we compute dFd? This is based on experiments, empirical experiments. So here I use D, I meant, like this small sectional. Okay, this is the velocity of the water particle, and this is the magnitude, the absolute value of this one. And this is the structure diameter, and this thing comes from experiment. And how do we compute the inertial force? I think Zhigang books, discussed the model test with you guys about the frictional coefficient, things like that, right? This is the acceleration, and this is the inertial coefficient. Is also from experiments. In fact, this is accounting for the added mass from for the structure. So then the total force on this small section, small element, is just the summation of the two. We had made an assumption, this is the inertial force. Those are in phase with the wave, the waves. That means the force is the forms like how do I see this in phase? Okay, and then the total force is what? Integration of dft, right? D from this bottom to the top minus d to 0, right? dz. Here ds it doesn't matter. It just it's dz. It's a integration diamond integral variable. So I can change this to dz, or I can change this to s, right? So this is the Morrison equation. So next time we're gonna discuss a little bit. So how do we find this? How do we look up those Morrison equation, the coefficients, and also the drawbacks of applying this, the limitations of this Morrison equation. Okay.